Yeah, now let us go for the next example. So this is it, and I have already done few calculations for you. I have already found out the eigenvalues. They are 0, 0, 1. Algebraic multiplicity of 0 is 2 and algebraic multiplicity of 1 is 1. So this is what I have started with, and first of all I am going to find geometric multiplicity of eigenvalue 0. So I have substituted lambda is equal to 0 in star. Therefore which system I will get here is 0, 0, 0, 0, 0, 0, minus 3, 0, minus 1, outside the bracket x, y, z is equal to 0, 0, 0. So I think there is no need of using Cramer's rule over here, and we should not use it also whenever the eigenvalues are repeated. No need of doing anything. So over here rank is 2, okay, which is less than 3, which is equal to number of unknowns. So rank is not 2. What it is 1, which is less than 3, which is equal to number of unknowns. Therefore the number of parameters that we should use over here is 2. Okay, so we have, what is our system? Our system is minus 3x minus z is equal to 0. And now where, for what variables we should use parameters? Now you should be very careful in this case. Don't use parameters for x and z. See, y variable is not visible, it means it is a free variable. So it is guaranteed that you should use one parameter for y variable and the other is flexible. So either you can use the second parameter for variable x or variable z, that choice is yours, but the first parameter should be used for variable y only. So I will say put y is equal to t, where this t belongs to r, okay, and z is equal to, I will put s, where this s is also a parameter. So therefore what will be your value of x? Okay, or shall I put for x? Yes, it will be better, right? So I will go for x, put x is equal to s, where s belongs to r. Therefore you will have 3s plus z will be equal to 0, I guess, and therefore z will be equal to minus 3s. Okay, so therefore what will be your e of 0? Okay, therefore my e of 0 in this case is, my value of x is s, my value of y is t, and my value of z is minus 3s. Okay, such that this s and t belongs to r now. Okay, okay, so which can be written as, now you're already familiar with this. First of all I will take t out, so what is left out? 0, 1, 0. Then I will take s out, then what is left out? 1, 0, minus 3, such that this t and s belongs to what? R. Okay, so therefore we got the basis of the eigenspace in this case. So therefore I will say the set 0, 1, 0 comma 1, 0, minus 3 is a basis, okay, of e of 0. And what are the eigenvectors? Okay, therefore you can say this 0, 1, 0 comma 1, 0, minus 3 are eigenvectors. Remember, these are linearly independent eigenvectors. Okay, are eigenvectors, okay, corresponding to eigenvalue 0. Okay, and therefore what is your GM? Okay, therefore your GM is 0. Okay, sorry, therefore your GM of 0 is 2. We can call it as some 2. Now for lambda is equal to what was the eigenvalue? The other one was 1, I guess. Okay, now keep it in mind that uh, since we got geometric multiplicity of 0 is equal to 2 and we got algebraic multiplicity of 0 is equal to 2, am of 1 is 1, so gm is going to be 1 only, no doubt. We will use Cramer's rule for that. So it is going to be diagonalizable, but we are doing the further calculations in order to find the matrix P, because they have said that if it is diagonalizable, then we have to find a non-singular matrix P such that P inverse AP is a diagonal matrix. So how to do that I will show you. Okay, so for lambda is equal to 1, so I am going to put lambda is equal to 1 in star. So I'll say put lambda is equal to 1 in star, and if you put lambda is equal to 1 in star, you will get 1, 0, 0, 0, 1, 0, minus 3, 0, it is going to be 0. Okay, outside x, y, z will be equal to 0, 0, and 0. Now I am going to use Cramer's rule for first and second row. Okay, so I will say by Cramer's rule, let us say what do we get. So x upon determinant of 0 0 1 0 minus y determinant of 1 0 0 0 which is equal to z upon determinant of 1 0 0 1 which is equal to t. Therefore x upon 0 which is equal to minus y upon 0 is equal to z upon 1 which is equal to t, and therefore you get x is equal to 0. Therefore x is equal to 0, y is equal to 0, and z is equal to t, where this t belongs to R. And therefore what is your E of 1? Therefore your E of 1 is 0 0, I guess t, but I will shortcut over here somewhat like this, such that t belongs to R. And therefore what is your basis? Therefore the set 0 0 1 is a basis, okay, is a basis of E of 1. And what is your eigenvector? Therefore the eigenvector is 0 0 1 is an eigenvector. Never say the eigenvector, is an eigenvector corresponding. So while using the in mathematics, you should be very sure whether it is unique or not. Otherwise better you use a or an if you are confused. Okay, is an eigenvector corresponding to eigenvalue, okay, 1. So now the question is how to find a non-singular matrix P. Okay, I'll therefore the GM of 1 is definitely, I'll write, therefore the GM of 1 is 1, I'll call it as some 3. Therefore from 1 2 and 3 you can say that, therefore from 1 2 and 3 we can say that A is diagonalizable, because AM of each eigenvalue is equal to what? GM of each eigenvalue. So now to find P. Okay, so finding P is very easy. Okay, so I'll say let P is equal to, okay, or directly, instead of saying let, here P is equal to, yes, okay. So simply put the eigenvectors, whatever eigenvectors you got, you have to put it in column form. Okay, so first of all, corresponding to 0 I got 0 1 0 and 1 0 minus 3. So 0 1 0 and 1 0 minus 3, and I think 0 0 1 was the other one, right? Let me check it once again. 0 1 0 1 0 minus 3, that's right, and last one is 0 0 1. Yeah, here P is equal to this is such that, okay, now this is important, P inverse AP is equal to the diagonal matrix. But which diagonal matrix? This is the question, and you should be careful. Now over here we are having a diagonal matrix, okay, 0 0. So the question is what should be the diagonal entries? The rest of the entries we already know, and the diagonal entries are, so never make this mistake. So diagonal entries depends on the order of your eigenvector. I will repeat again. So this diagonal entries depends on the order of the eigenvector. So since the first two eigenvectors are corresponding to eigenvalue 0, therefore first of all I should write 0 0, and at last you are having the eigenvector corresponding to eigenvalue 1. So over here I should write eigenvalue 1. So actually diagonally you are having eigenvalues only, but the order of the eigenvalues depends on the order of the eigenvector. Suppose जर मी 0 0 1 आधी लिहिलं आणि ह्या दोन eigenvectors जर इकडे लिहिल्या, सपोज स्वॅप केलं, then what will changes? इथे 1 येणार आणि इथे काय येणार? 0. Is that okay? So you should be very careful. Okay, आणि डिस्टिंक्ट eigenvalue च्या केस मध्ये पण आयडिया क्लिअर झाली असेल. जर eigenvalues डिस्टिंक्ट असतील आणि whatever eigenvectors you got, so the maintain the order of the eigenvalues on this diagonal. So P ह्या मॅट्रिक्स मध्ये eigenvectors तुम्ही ज्या ऑर्डरने लिहिता त्याच ऑर्डरने इथे eigenvalues आल्या पाहिजे. Okay, so this is the important thing to note. So that's all about this example then. So I hope now you will be able to solve the examples on diagonalizable